Hello everybody, my name is Dmitry and today we're going to work on determination of organic structure. This is the first video of the course and today's molecule is going to be easy for us. Let's get started. In order to determine the structure of the organic formula, we will use proton NMR, two types of carbon NMR, DEPT and normal carbon, mass spectrum, mass spectrometry and IR. So this is a study task and we'll consider not all elements, only carbon, proton, oxygen, nitrogen, halogens and sulfur. We'll start with determination of number of carbon and protons in the molecule. Maximum number of carbons we can calculate based on mass spectrum. We know that that molecular ion is 74 gram per mole, and if we divide 74 by 12, we'll have 6 carbons maximum. We'll mention here. As for minimum number, we can see on carbon NMR, so we can see 3 distinctive signals which says that we have at least 3 different carbons. As for protons, we should use proton NMR. So we have 3 signals over here, and integrals have ratio 1 by 2 by 3, which means we have at least 6 different protons, and we can also use the formula below, which let us calculate maximum number of protons. So maximum number of carbons is 6, 6 by 2 is 12, plus 2 is 14. This is maximum number of protons based on valency of carbon, which is always 4 in organic, almost always 4 in organic compounds. But the number which we calculate over here should be multiple of 6, so which means we cannot write 14 but 12. Then we should see whether we have chlorines and bromines in our molecule. This is pretty easy to see with mass spectrometry. On the right you can see distribution of natural distribution of isotopes of the elements we expect in our molecule, and the most important is chlorine and bromine. Why? Because there is not only one prevailing isotope naturally. In case of chlorine, it's 35 and 37, and 37 is about quarter of all chlorines in nature. As for bromine, it's even harder. It's even half of 75, 79 and half of 81 bromine, which is actually very significant. And of course we don't have bromine because of our mass of molecular ion is 74, bromine is heavier. But we may have chlorine. Let's take a look at the mass spectrum. In case we have chlorine, we would see 2 molecular ions with masses 74 and 76, because difference between these 2 isotopes of chlorine is 2 gram per moles, so mass plus 2. And ratio of these signals, intensity ratio of intensities of these signals should be exactly the same as we can see in natural distribution of the isotopes of chlorine, which means 3 by 1. We may have a small signal, maybe it's 75, but it's definitely not 76, and ratio is definitely not 3 by 1, which means we have no chlorine in our molecule, which makes it even easier for us. So no chlorines, no bromines, and we go further. Then we should look at the proton NMR. We have 3 signals. We'll start with this triplet around 1 ppm. This triplet means that we have protons which can split on 2 other NMR equivalent protons. So we have triplet which corresponds to our protons, and it has a neighboring carbon with 2 NMR equivalent protons. So we can draw this moiety over here. So we have some number of protons, and we know that this is an integral of 3, which means we have 3 protons, and they split on 2 others. So in this case, we are talking about these 3. This is a signal of these 3. Perfect. So we go the next. The next we have a quartet at around 2.5. Quartet means that we have some protons which can split on 3 different protons, which means we have we have this situation. We have protons which give us coated, and these protons split on 3 other NMR equivalent protons. We can also draw it this way. So in our case, we have actually the opposite situation compared to the other one. So we're talking about these blue protons. We just skip black ones. So in the last signal we have is singlet at around 11. This is a broad singlet, and usually it means that it's either OH group or NH2. It doesn't seem to be amino group, but more hydroxy, because it's too shielded. Around 11, it should be oxygen. So we can draw it this way. So we have one proton, and we have some other atom. We don't know exactly what the atom is. It is, but it looks to be oxygen, as we said before. So, and we have these proton parts. We cannot say whether these 2 protons are those 2. We cannot say. It looks to be that they split on each other, but not necessarily. So let's go to carbon NMR. We have normal carbon and we have the DEPT carbon. DEPT can show us CH3 and CH groups, which are on the upper part of the spectrum, and CH2, which are below. We see that we have one type of CH2 group and one type of CH3 or CH. Based on our proton spectrum, we didn't see CH groups, so it was CH2 and CH3 only, so which means this signal corresponds to CH3 and the other one is CH2. So, and basically we get the same information in carbon NMR as we got in proton. The next what we should do is to calculate the rest of the molar mass. We know that our molecule has some parts, some moieties, and we can just deduct all of them and calculate what we have rest. So we have molecular iron which is 74, we deduct CH3 which is 15, we deduct CH2 which is 14. We also see one carbon which has no protons on it, because we don't see it in DEPT, but we see it in regular carbon, which means we should deduct 12 also. So we deduct also 12. What we can see, we see 33. So it's not that many things which can be at 33, but we mentioned that we may have oxygen because of this very broad singlet in proton NMR. So, and 33 actually corresponds to 2 oxygens and 1 proton. So we say that it's 33, it's 2 oxygens, and it's 1 proton. So it looks that we have a carboxylic group, because we have absolutely substituted carbon, we have 2 oxygens, we have 1 proton, and I think you already guess what the structure we have. Of course, it's propionic acid. So if we bind 1 carboxylic group over here, we'll get the molecule which we discussed about. So we know everything. Let's make it blue. Additionally, we can check some other things. For example, we should see whether this carbon signal at around 170 really fits carboxylic group. We can do it here. So we have around 170, so which is here, and we see that, yeah, it can be carboxylic group. So it's actually correct. Also, we can see whether this signal at 11 of proton NMR also fits it. So we are scrolling down. 11, yeah, it's proton on carboxylic group. Additionally, we can also check IR spectrum. We see that we have very distinctive signal at 1715. We should see whether it also fits our functional groups in the molecule, which is carboxylic group. 1715. Yeah, it also looks to be carboxyl group. So this is also correct. And the last thing we can also do, we can check whether differences between molecular ion and the masses we see in the mass spectrum really fit parts of our molecule. So we have molecular ion, which is 74, we deduct 57, and we have 17. So let's see what we can observe at 17, OH plus. So we have H group in the molecule, which is correct. Then 74 minus 45, so we have 29. 29 gives us ethyl cation, and we also have ethyl group. This is also correct. Actually, we determine the structure, and to make for 100% sure, we can do determination of the structure in the program MS Tranova. We'll just copy this molecule, paste it into the program, and we can ask the program for prediction. So what we can see in the prediction spectrum, we don't see the proton carboxylic group, but MS Tranova just doesn't show range above 10 ppm, so we don't see it. But we can clearly see our quartet at around 2.4. In our case, it's also around that range, and triplet at around 1 something, so it actually fits. And prediction says exactly the same proton signals. As for carbon, let's check the carbon also. Carbon says that we should have signal at around 180. We have 170, 180, yeah. And also two other signals, 20 something and around 10. This is basically what we have. This is basically the same. We finished with the determination of the molecule. If you like this video, give a thumb up or leave a comment. See you soon with the next molecule.